Hello, everybody. Good morning, good afternoon, good evening. For those of you joining us across the globe, my name is Dara Mulligan. I'm a technical marketing engineer here at AMD. My responsibilities include managing the power delivery partnerships that AMD has, building power reference designs, and breaking down the barriers between customers and successful power delivery design when it comes to define power for their devices, for all AMD devices. So I'll jump right into it. The Spartan brand is one of the most well-recognized brands in FPGA history, and for good reason. We first introduced Spartan back in 1998, and the philosophy behind it then has been to take forward-looking features and put them into a cost-optimized device meant to last for decades. Because of that, Spartan FPGAs are some of the most widely adopted FPGAs across almost every industry and in too many applications to count. Given that breadth, our customers have done some amazing things with Spartan FPGAs over the years, from healthcare solutions like automated external defibrillators to surgical robots, supporting green energy solutions, and understanding the fundamental laws of physics at CERN with the Large Hadron Collider. It's clear that the Spartan brand continues to impact all of us in our everyday lives. AMD's cost-optimized portfolio consists of versatile FPGAs, contributing to many applications from automotive ADAS and LiDAR for real-time image classification and object detection, to industrial vision and healthcare, bringing processing power for the ultrasound engine, as well as audio-video broadcast, providing 4K video for video collaboration with high bandwidth, low latency, and reliable video quality. These examples span across different industries, showing the versatility and adaptability of our products. It could also include applications like machine vision for quality control and manufacturing, edge computing for real-time data processing, factory automation for efficient industrial operations, and medical devices for accurate diagnosing and monitoring. These applications not only exhibit diverse functionality of our FPGAs, but also underscore how they are empowering innovation across sectors. The growth of IoT devices and sensors at the edge is predicted to expand significantly by a factor of 2.3x from 2022 to 2028. This growth represents both exciting opportunities and challenges for industries across the board. Research indicates that there is currently a 30% deficit of design engineers available in the market. This gap is creating significant strain on development processes and project timelines. Given this shortage, it's imperative that developer efficiency improves. There is emphasis on the continued need for supply chain stability and longevity. As industries evolve, having a resilient supply chain becomes vital for sustained success, requiring production ramp that typically spans 4 to 6 years, and in many industrial markets, we are seeing life cycles that exceed 15 years. Spartan UltraScale Plus delivers high I/O density, low power, and state-of-the-art security features. It offers the highest I/O to logic cell ratio in the industry for FPGAs designed with the 28 nanometer or newer nodes, with 3.5 times more I/O per logic than prior generation Spartan 7 devices. This is critical for I/O intensive applications as it allows customers to do more in a smaller part, reducing overall cost, footprint, and power. On power, Spartan UltraScale Plus is built on the 16 nanometer process node, delivering up to 30% reduction in total power compared to prior generation 28 nanometer devices. Combine that with hardened interfacing IP for DDR and PCIe on the larger devices, you can see an improvement in interfacing efficiency as well. We've also raised the bar in security. Security is a continually evolving area. Many customers are asking us how they can protect their IP and prevent tampering, and honestly, the answer to that changes over time. For example, with advances in quantum computing, the methods we use for secure authentication, namely RSA, are changing. To keep up with the latest advances, Spartan UltraScale Plus uses NIST-approved algorithms for post-quantum cryptography. With the help of our tools, AMD has an edge on maximizing developers' efficiency. The quality and efficiency of the tools and documentation play a critical role in that. This has always been an area of strength for us, so in some sense it's nothing new for AMD, but that's not true across the industry. One area in particular, as a single integrated design tool, does two things. It means customers don't have to juggle multiple tools from multiple vendors when trying to design for a single device. It also means same tool across the portfolio from low-density devices to high-end Versal. Finally, AMD, through the acquisition of Xilinx, has been in the FPGA market for nearly 40 years, with literally billions of devices shipped. Hard to beat that kind of track record for stability. From a product perspective, we strive to support greater than 15 years product lifecycle. One of the reasons for choosing 16 nanometer for Spartan UltraScale Plus is applications where lifecycle is absolutely critical to our customers. We wanted a family that would be as long-lived as some of the classics. Now focusing on device features. On the left, you can see Spartan UltraScale Plus is built on the proven 16 nanometer FinFET technology, and compared to previous generations, this enables power reduction, where we're able to reduce power by hardening some IPs such as the memory controller and PCIe. Higher total on-chip memory is achieved by adding more storage with the support of UltraRAM. It also enables faster transceivers up to 16.3 gigabits per second, enhanced performance and power efficiency of PCIe interfaces as hardened IP up to Gen 4. And also, the 16 nanometer FinFET process allows for faster and more efficient digital signal processing up to 384 DSP48E2. On the right, you can see that Spartan UltraScale Plus is getting some new capabilities intended to enable cost-sensitive customers over the long run. Starting with the flexible I/O interfaces with 3 different types of I/O up to 3.3 volt and supporting 3.2 gig MIPI D-PHY. State-of-the-art security features as post-quantum crypto with NIST-approved algorithms, AES GCM for speedy, secure configuration, and PUF for unique device identification. In addition to that, supporting hardened memory controller with LPDDR4X and LPDDR5, and considering the lifecycle of memory types, supporting LPDDR5 is key for longevity. We offer packaging as small as 10 by 10 millimeter chip scale packaging with improved thermal and electrical performance, ideal for space-constrained applications, whereas ball grid array allows for more I/O connections, beneficial for complex, high pin count applications. Spartan UltraScale Plus continues the multi-node power reduction trajectory. Built using TSMC's 16 nanometer high performance, low power FinFET technology, and leveraging our almost decade-long experience with that process node, we are able to offer lower static and dynamic power at this node compared to previous cost-optimized families. By comparing Spartan UltraScale Plus at 16 nanometer with Spartan 6 at 45 nanometer and Arctic 7 at 28 nanometer, we can see that the power savings when using apples-to-apples comparisons for a 200 megahertz design in each device. From Spartan 6, we have a 40 and 60% reduction versus Arctic 7 and Spartan UltraScale Plus. Some of the other ways we've been able to lower dynamic power is through efficient logic packing and enhanced local routability, where more control set flexibility allows for an improved place and route algorithm, leading to reduced wire length. This also reduces interconnect capacitance power, significantly further reducing overall power. Power is one area where lower is always better. And on Spartan UltraScale Plus, we achieve power efficiency in 2 primary ways. First, the move to 16 nanometer gets us up to a 30% reduction in total power when looking at the lower density devices. This 30% is not consistent throughout the full portfolio. In fact, for larger devices, the static power goes up with the addition of hard IPs. We carefully thought about this and wanted to help you position the power for the larger devices with integrated hard IP. We're able to achieve up to 60% lower power for interfacing, looking specifically at power efficiency measured as total power per bit transferred on PCIe or DDR, in addition to more memory and PCI bandwidth compared to 28 nanometer. So the move to 16 nanometer gets us a nice improvement in power for the FPGA fabric, and the hardening of key IP gets us an improvement in power efficiency for interfacing. There's actually a third way to further improve power savings. Because we're using our 16 nanometer fabric, our benchmarking is also showing up to 1.9 times fabric performance. Most customers in the cost optimized space don't care as much about raw performance, but customers can use this performance to run their design at a higher clock rate and save resources. This will actually allow customers to fit the design into a smaller part, saving even more power. One of the areas where we accelerate performance and power gains, increase the density of a device, and free up programmable logic for user design is by hardening critical interfaces. Hardening refers to taking something that was originally a soft IP that had to be implemented in programmable logic and hardening it into the silicon itself. There are numerous benefits of hardening, such as offering higher frequency in the PL, simplifying time enclosure, increasing performance and power ratio, and giving users back more programmable logic for their designs. This process also decreases the picojoule per bit power of the interface, which can be seen as the cost of getting data into and out of the device. For Spartan UltraScale Plus, the memory controller has been hardened, moving from DDR3 at 800 megabits per second to LPDDR4X at 4,266 megabits per second, presenting a significant interface upgrade. This transition results in 75% lower power on the picojoule per bit. Another critical interface is PCIe, where we have shifted from a Gen 2x8 to Gen 4x8, leading to substantial increase in performance and a 60% reduction in picojoule per bit power. By offering these hardened IPs, greater power savings can be achieved alongside a range of other benefits. Programmable logic resources are freed up for user design, and timing is simplified as the hard IP is not programmable, does not need timing closed. The final aspect to consider is how to read and transfer data from these faster interfaces if the fabric performance does not keep up. To address this issue, the Spartan UltraScale Plus series has significantly increased the performance of the fabric. When it comes to power delivery design for cost-optimized applications, ensuring our customers have access to industry-leading power delivery solutions that are optimized for cost, efficiency, and space is critical. Our Power Design Manager tool is a highly comprehensive and efficient tool to help you with your power estimation and power delivery definition. The tool features dynamic decoupling capacitor calculations and recommended part numbers based on the user design, power sequencing information, sequence diagrams, and rail consolidation images to help reduce the number of regulators required. We break down power estimations by static and dynamic currents, helping you with part selection and understanding of the block level power contributions. Some of the recent updates for the Power Design Manager include in Vivado 24.2, full power rail support for Spartan UltraScale Plus, detailing voltage levels, current requirements, and more. In Vivado 25.1 release, enhanced power design support for efficient delivery and decoupling, serving as a power datasheet. The Power Design tab will simplify power delivery with rail consolidation, calculated decoupling capacitors, and complete sequencing information based on design dynamics and utilization. When it comes time to define your power delivery, we have a wealth of resources available to help you minimize risk and shorten time to market. For Spartan UltraScale Plus, we focus on low-cost, minimal BOM, and high-channel integration type solutions to reduce cost and complexity of your power delivery. Our reference designs for cost-optimized devices have been designed for the target markets featuring low cost, small size, and high current density. These solutions use high switching frequencies, allowing for smaller inductors, and also use LDOs to power low current rails. Telemetry can also be used for powering down regulators for sleep modes or battery-powered applications. Power management ICs, or PMICs, can also be leveraged to integrate many regulator outputs in a single IC when board space is low. PMICs often have multiple switching outputs as well as integrated LDOs to shrink board size and BOM count. Depending on the power IC selected, some PMIC channels can be combined to increase current output capabilities for added flexibility. Power modules are another type of solution that integrate into inductors, resistors, and capacitors to reduce solution complexity, simplify layout, and reducing overall BOM. In addition, low-cost power modules provided by MPS are flexible in board placement and can shrink overall solution size. I recommend you view our webinar with MPS, where we demonstrate power management for our cost-optimized devices and MPS low-cost power modules from last year. You can find cost-optimized power reference designs and more design resources on amd.com/power. Also, keep an eye out for Spartan UltraScale Plus power reference designs coming second half of this year. Allow me to unveil the Spartan UltraScale Plus family product table, highlighting some of the important features. We have 9 devices ranging from 11K logic cells to 218K logic cells. This overlaps with the Spartan 6, Spartan 7, and Arctic 7 logic densities and fills the gap with lower densities we had with the Arctic's UltraScale Plus family. As the industry's highest I/O to logic cell ratio for new nodes FPGA, you can see the smallest device has a package with 304 I/Os and up to 572 I/Os with the largest package. You will spot here that the smaller devices has the highest I/O to logic cell ratio, making them suitable for glue logic and I/O expansion, as well as board management controller applications. While for the larger density devices suitable for edge sensing, control applications which require the use of PCIe and transceivers. The PCIe interface allows for faster data transfer, crucial for real-time edge sensing applications. Meanwhile, transceivers handle the high-speed serial communication. The family comes with a small 10 by 10 millimeter package that are perfect for applications with space constraints, such as wearables, cameras, IoT devices, and compact industrial controls. The SU10P, SU25P, and SU35P devices are now in production with production level power estimation in our Power Design Manager tool. The larger SU150P and SU200P devices with hardened DDR-MC and PCIe will begin sampling in the second half of this year. Here we can see the Spartan UltraScale Plus evaluation board roadmap and a list of the features each board provides. The SCU35 uses an SU35P device and is targeted for I/O expansion, boasting 64 megabits of hyper-RAM, as well as PMOD, Raspberry Pi Hat, and Arduino connectors for added expansion. This board is available now in early access, but will be available to the public in Q4 of this year. The SCU200 uses an SU200P device and is targeted at edge sensing and control with PCIe 4x4 and LPDDR5 support, as well as PMOD, FMC, and a 40-pin expansion header. This board is expected in the first half of next year. I'm also delighted to announce that we have selected MPS as the power delivery solution for the SCU35 Spartan UltraScale Plus for their low-cost and small-size solutions, which is aligned with the cost-optimized goals of Spartan UltraScale Plus. Finally, we're excited to announce that the commercial SU10P, SU25P, and SU35P devices have been released to production since May this year. All related documentation is publicly available in the AMD Technical Information Portal for your convenience. Many of these devices are in stock today, with evaluation boards shipping soon. SU10P, SU25P, and SU35P are also supported in AMD Vivado Standard Edition 2025.1, as well as Power Design Manager, providing enhanced capabilities for your design needs. Looking to the future, SU200P is currently in beta, so we recommend speaking to your field application engineer for more information on that. All right, and with that, I'll hand you over to Nikolay, who's going to take the MPS Power Modules portion of this webinar. Thank you.
Thank you, Dara. Let me quickly share the screen. It was a very nice presentation showcasing the new Spartan UltraScale Plus. Now we're going to talk about the power and how we are able to address the key points of powering the FPGAs. So my name is Nikolay Garcia. I'm an applications engineer for the Power Modules team at MPS. Today we're going to talk about the power solutions for the Spartan UltraScale Plus and other FPGAs. And thanks for joining. So I'd like to start our presentation with a traditional introduction to MPS. MPS is an American-founded company with a headquarters in Kirkland, Washington State, and with a global presence. I'm based in Barcelona, where we have an R&D lab and a lot of applications engineers dedicated to many MPS teams. And it's one of our largest European offices. Speaking about the series of product families, we have a wide portfolio of products that include AC to DC converters, DC to DC converters, automotive and industrial solutions, isolation, power modules, battery management systems, and so down and so forth. Coming from the Power Modules team, we believe that the future of powering the FPGAs in fully integrated power solutions for several key advantages. First of all, the full integration. As Dara have mentioned, the inductor and some other components, for example, the bootstrap capacitor, are integrated inside one package. So at the end, what you have an overall small size, reduced amount of BOM count. You only need to place input and output capacitors on the board, which also makes it very simple and easy to integrate in your current solutions. The next and a very important point also is the advanced control methods, like the constant on-time control MPS patented. It allows us to achieve fast transient response, and precise regulation of the output voltage. Another advantage that comes to the modules is since the solution is fully integrated, we actually have smaller hot loops and the ability to manage them with minimum impact on system performance, which results in overall less noise and more stability. MPS power modules meet Class B EMC and AMI emissions, which results in fast time to market with a full qualification, which is great for fast prototyping and launching new products. Speaking about the power modules applications, nowadays MPS power modules are widely used in the key areas of today's world industry, like the data centers and AI, test equipment, drones and robotics, industrial applications, automotive solutions, aerospace and defense, and of course FPGAs. Actually, we can divide FPGAs into two different categories. First would be the high current, which has those kind of applications like data centers, AI solutions, industrial and test equipment, which means high current rails and usually high input voltage. And the low current applications, like there I've mentioned in the AMD part of this webinar, this results in having robotics, LiDAR platforms, video signal broadcasting, medical imaging, video processing. This is all done by the FPGAs with low current rails. So for instance, for the Spartan UltraScale+ specifications, this table outlines the specific voltage and current requirements for the Spartan UltraScale+. As we can see here, the overall voltage rails are having the low voltage and precise voltage tolerance, ±3% for every rail of the FPGA, with the load current varying from 0.25 amps to 2.5 amps. In addition to that, it's important to address that 1% DC voltage set point and ±2% for the AC set point ripple has to be maintained. So with this being said, we arrive to the pivotal moment where we define the FPGA power constraints and what are the actual designer needs. As an expert in the field, we know that designers face multiple challenges when powering FPGAs because the FPGAs require precise voltage regulation, which already been mentioned, ±3% is a standard now, and it's getting closer to ±1%. Large power trees, we need to reduce the amount of components on our PCB because we also operate in the limited space-constrained applications, usually involve FPGAs. And low core voltages, as we saw in the previous table, the core voltages for those kind of FPGAs are usually 0.85, 0.72 volts. So the designer needs are straightforward. We need precise voltage regulation, small solution size, simple and flexible designs with high efficiency. Starting with precise voltage regulation, as we know for the Spartan UltraScale+, the transient response has to be very fast, up to 100 amps per microsecond with 25% load for the core rail. And overall, we need to maintain up to ±3% tolerance for every rail of FPGA. So how we can do that? If we compare in this slide the current standard control scheme and the constant on-time control, which means that we're comparing peak current mode with constant on-time, we can see that the industry standard doesn't allow to achieve the fast response that is required by modern FPGAs. One of the factors that slows down the current mode control is the switching cycle delay caused by internal clock that feeds the pulse width modulation control to the output MOSFETs. The control frequency is fixed, so that means it is also determined by the clock period. While we can receive a signal from an error amplifier relatively fast, the whole circuit needs to wait for a new clock cycle to deliver power. If, like in this case, the current spikes up straight away after the MOSFET are switched off. So that means we need to wait all of this time to deliver power again. While this is happening, our output voltage drops and we can see the undervoltage happening because the energy needs to be delivered and it's delivered from the output capacitors. So with this being said, we not only get an undervoltage, but we also lose some performance and efficiency because then those capacitors needs to be charged all over again. Conversely, the constant on-time control doesn't use a clock. What we do here is when the Vout falls to the level of threshold we set, we inject multiple pulses with fixed period, which reduce the delay between the cycles. We actually have the fixed period of those pulses. That's why it's called constant on time. And this allows us to achieve fast response and precise regulation because we do not fall behind the under voltage threshold. Speaking about this, for example, with the NPM 54304, we can see with the input voltage of 12 volts and the output voltage for single channel of 0.85 volts, the transient test from 0 amps to 3 amps, which is a maximum current for this rail, we are able to achieve the output peak-to-peak voltage of 66 millivolts, which is within the 3% and allows us to be classified for the tight output voltage regulation for those FPGAs. It's important to address that 0 to 100% of the maximum current is achieved with only two 22 microfarad capacitor per channel. With this being said, we can see that the key advantage here is overall reduced amount of output capacitors, fast transient response, and stable output voltage. The next piece of the designer need puzzle is small solution size. This can be addressed by using MPS PMIC power modules. Those products involve multiple output channels and are available in a compact package. That means that for the Spartan UltraScale+, we can use a single device to power every rail of our FPGA. It's important to note that FPGAs come in different SKUs, so the amount of actual rails can vary from application to application. If we use NPM 54304, we even have an extra spare rail that can be used for additional VCCO voltage or periphery according to the application needs. So speaking about the NPM 54304, it's a quad PMIC power module which has two 3-amp channels and two 2-amp channels. It brings a lot of flexibility to the design because it has an I2C interface which allows you to configure the device according to your specific needs. The output channels can be parallel to achieve higher output current. The input and output telemetry is available to constantly check the parameters of the system. And what is also very important for FPGAs is that it is available in ultra-thin LGA 7x7 package, which results in the comparison between the traditional PMIC and PMIC power module, allowing us to save up to 81% of board space because 4 inductors are integrated in one package. In addition to that, it's important to notice that there are other parts available with higher power at the output with the same advantages of design flexibility, I2C interface, and so down and so forth. The next step is simplicity and design flexibility. To address this, we implement two separate things. First of all is the virtual bench guided user interface. Second thing is the reference designs. Starting with virtual bench Pro 4, it's a MPS guided user interface we use to program our parts. MPS parts and power modules supports I2C and PM bus protocol. It is very easy to monitor the real-time data, the input voltage, the output voltage, the temperature, and so down the line. You can also evaluate everything totally offline, no need of the internet connection to operate with MPS Virtual Bench. What is also great is that at the end, once you configured the device parameters according to your application, you can export your settings and then purchase your custom pre-configured parts. This results in a very fast evaluation and prototyping. So for example, it is very easy to set up the soft start time with Virtual Bench. In the right corner, you can see the video of me setting up the startup delay, which is very helpful for FPGA applications. The process is very straightforward. You need to launch the Virtual Bench guided user interface, scan for connected devices, select the part number from the list of available parts. Then you just select the required output or the buck converter, go to the power on-off menu, and in the pull-up menu, you select the desired soft start delay time from the list. After this, you can save your configuration into volatile memory. This is good for a fast prototyping and evaluation. Or when you're sure, you can save it to non-volatile memory, which will require a power cycle for the implemented changes. It's important to note that some parts have multiple remaining cycles for non-volatile memory. Some parts, like MPM 54304, has 2 cycles. So speaking about the configuration, for instance, in this scope, we can see that the soft start time is set to 0 when the enabled signal is pulled high. We can see that both Vout1 and Vout2 are starting up simultaneously. Conversely, for the part that I've set up, we can see that the soft start for channel 1 is 1 millisecond and soft start for channel 2 is 3 milliseconds. So this is the delay we can see between actual Vout1 and Vout2 when enable is pulled high. The next thing that allows us to make the designs simple and flexible is FPGA's reference design. MPS has a wide portfolio of reference designs with partnership with AMD. Not only we are working with the Spartan series, but with Virtual Sync and many more. And what is great about this, that you can find the solution that will fit your application. It can be size optimized, efficiency optimized, cost optimized, PMIC power solution, or something that will address your needs. In addition to that, now we have a dedicated page on our main website that will lead directly to the FPGA power solution where you can find the reference designs. So last but not least is the efficiency. The power solutions that power FPGAs need to be efficient. Speaking about the Spartan UltraScale+, as already been mentioned, we are using single device to power all the rails of the FPGA. And we can do this with 12 volts at the input while delivering the power to the output with the efficiency in range of 80 to 90%. Speaking about the 4 output channels, we are able to deliver total power of 26.1 watts at the 88% efficiency with a maximum heat of 72.2 degrees Celsius. So to summarize, the designer needs are precise voltage regulation, small solution size, simplicity and design flexibility, and high efficiency. All of those parameters can be achieved if you use AMD Spartan FPGA series and MPS power modules that are powering the device. In addition to that, today we talked about only 2 MPS parts, MPS PMIC modules. The portfolio of power module series is way larger than that. You can see that we have multiple products for low voltage, high current, low current applications, which can help you build your solutions with the FPGAs. I would like to also mention the MPS Now team and our reference design team. There is a dedicated team of engineers with MPS Now that are constantly working on answering customer questions, and you can access those with the platform on our website or just simply send an email for the global support mpsnow@monolithicpower.com or European Union support EU mpsnow@monolithicpower.com. In addition to that, if you have any questions regarding the reference designs, you can send an email to the referencedesign@monolithicpower.com. Thank you for joining today's webinar. I think now it's a great time to answer the questions.
Thanks a lot, Nikolay and Dara. Really great presentation. So just remind everyone, you can scroll over the bottom of your Zoom webinar interface and you will be able to see the Q&A button. So please type in any questions you might have. Okay, I see more questions coming in. So let's get started with the first question. It's for MPS. So Nikolay, can the adjustable features be configured via I2C interface and the GUI you've mentioned, and subsequently be used for a customized order?
Thanks, Lydia. It's a great question. Happy to answer that. So as I've mentioned, the I2C interface allows to adjust the parameters of the module you are working with. And for instance, the NPM 54304 has two MTP cycles. One MTP cycle is for the factory setup, another one is for the customer. And then when you, for example, decided to change some of the parameters of your system, you can save, lock the new configuration, and then contact your MPS representative, which can help you to build a custom suffix for your part. What we do is we generate the custom suffix which is going to be assigned directly to the customer and is not going to be used by someone else. And this helps you to then pre-purchase the pre-configured version. In addition to that, everything is managed by MPS, so the only thing you need to do is to define the parameters of your system, export the settings, and then provide it to the contact person in MPS.
The second question I have is for AMD. With the introduction of Spartan US Plus devices, will we start to see older Spartan 7 devices wind down?
Yeah, it's a very good question. Not at all. So we're still very much committed to the 7 series of devices that we have. Like we mentioned earlier in the slides, longevity and trust with our customers is very important for these devices, especially if they're committing to using like a Spartan UltraScale Plus or a Spartan 7 device. In fact, the 7 series FPGAs and adaptive SoCs, their lifespan is being extended through to 2040. And the AMD UltraScale Plus FPGAs and adaptive SoCs are being extended until 2045. So there's quite a lot of future for these devices, I would say.
Thank you. And one more question for you, Darren. So are there any additional means of saving power in Spartan US Plus beyond the power reduction due to the 16 nanometer process?
Yeah, there is actually, now that you mention it. So you can power down the voltage regulators when the device is not in use, but you can also, within the actual Spartan UltraScale Plus device itself, gate the clock, which means it disconnects it from the circuitry, which would be switching within the device and processing. So this doesn't actually require any powering down of the voltage regulators. You can also scale the clock to a lower speed, which would reduce power, but would also have an impact on performance. But all these methods are available within our device, which is very convenient. We actually have a white paper on this called White Paper 370. So you can check that out for more information.
Yes, thank you. And question for MPS. The FPGA require power up and power down sequencing. How can you handle power sequencing like up and down?
Thanks, Lydia. So MPS power modules have a built-in startup and shutdown sequencing. As we discussed, the startup is relatively straightforward. What we can do is through the PM bus and I2C interface, we can program the soft start delay, and it allows us to start our integrated box later on with the delays we preset. Regarding the shutdown, what we can do is select between two modes of shutdown sequencing. To do that, we need to simply change the value of the corresponding register. If I'm not mistaken, it is the shutdown delay enable for the NPM 54304. So when the value of this register is set to 0, all the DC outputs power off at the same time. On the other hand, when the value of the shutdown delay is set to 1, the part goes in so-called power off sequence mode. The NPM 54304 supports the controlled power off through the enable pin. When the enable pin is pulled low, the system enters the power off sequence mode, during which the power good is also pulled low simultaneously with the enable signal, before the device starts to turn off the DC outputs. In order to fully discharge the output voltage, the enable signal is blanked, so to speak. During this period, the NPM 54304 continues working in the output discharge, regardless of whether the external enable pin is pulled high or low. So no matter if there is going to be a signal, sorry, that was a mistake. So no matter if there's going to be a signal of enable, first the device will finish the power off sequence, protecting the FPGA from the inrush currents and so down the line. And then the DC power off sequence works in reverse to the power on sequence. So we discharge all the capacitors in a sequence that we start up. That will also help to improve reliability and protect the FPGA from potential damage.
Thank you, Nikolay. Another question I'm seeing is for AMD. I think it's during Dara's presentation. Could you explain further hardening and why it's better? Dara, if you could shed some light on the questions and provide the answer. Thank you.
Yeah, sure. So hardening refers to taking what is traditionally a soft IP, which is implemented in the programmable logic of our devices. And because it's programmable logic, there's extra gates and extra circuitry and lookup tables that are required to actually implement that IP in programmable logic. If we harden it, it's closer to what traditional silicon looks like, so we can remove a lot of those additional circuits that are necessary for the fabric. We can also, reduce the need to close timing because there's no race conditions that are happening within the device. So it's still configurable to an extent, but not to the extent that programmable logic traditionally would be. But of course, you get the benefits of all the power savings and quality of results for the rest of your design.
Great, thank you. And one more question we have is there any solution for Verso Gen 2 Prime devices? I think this
Yes,
question. Yeah, please
they're
go ahead.
actually in development at the moment. MPS is developing some hardware verified power reference designs for Versal AI Edge Gen 2 and Versal Prime Gen 2. So we expect those will be available publicly in the coming months. We don't have a hard date right now, but I recommend you check the website, amd.com/power. That's where they'll be updated or uploaded to. And also check in with MPS, and they might be able to give you more details at this point.
Thank you, Dara. I see our last question here is for MPS. What about the derating factor of NPM 54304? Thomas,
Yeah.
if you could provide the answer to us, or Nikolay, yeah, please go ahead.
Yeah, so for the parts, thank you for the question. I think for the parts that are currently available, we have also the datasheets published on our website, and the derating or the power loss over temperature plots are usually available in the documentation at the page 12, if I'm not mistaken. So it also highly depends on the application and the ambient temperature you're using. I think it's important to address the application and the conditions where the power is used and align it with the data from the documentation. Thank you.
All right, so at the moment, I'm not seeing any further questions. As I mentioned before, the presentation and the link of the on-demand version of the session will be sent out in the next few days. So all attendees can review at your convenience. Feel free to share with your colleague or other people who will benefit from the content. If you're interested in more webinar links like this, feel free to check out our website, monolithicpower.com/support/webinars. So stay tuned for our future webinars. We have plenty more interesting topics coming up. With that, I would like to thank you everyone for joining our webinar live today. We hope to see you again very soon in the upcoming ones. Thank you. Have a great day.